So for example, if you had like a 1 molar of SROH2, when you put this in water, it breaks into SR and 2 OHs, right?
Oh, so you would multiply by the 2.
That by 2, yeah. So you need to take, so instead of 1 molar, you would take the pH of a 2 molar.
Oh, okay.
Does that make sense?
Yeah, thank you.
I can't erase anymore either. Wow. My computer's doing awesome today. Okay. Yeah, so it's a really, really simple thing, just people seem to forget it. Just because we do so many things that are so much more difficult. So I think people just kind of forget some of the simple stuff sometimes. Okay, so we're going to look at the strength of binary acids. So we're going to look at the strength of all acids. So we're going to rank the strength. We're going to rank the strength of acids. Rate the strength of acids for the next few minutes. So if it's a binary acid, it's really going to be polarity and bond strength. That's what's going to make the biggest difference. So the more polarized the bond, the more acidic the bond is. Because the more polarized it is, the easier it is to pull it off. So I don't have a pointer. Every time I use my pointer, it's now a pen. All right, I'm going to have to try and figure this out. My computer is in rare form right now. So the stronger the bond between the hydrogen and the ion, sorry, let me make sure you guys can see me. So the stronger the bond between the hydrogen and the ion is, the weaker the acid is because it's being held together stronger. So like, for example, like HF, if you look like, so let's go across the period. Let's look at like water and HF. So when you look here, the increasing electronegativity, so this is holding, the F is holding the H tighter to it, right? Because it's a bigger difference in electronegativity. So because it's holding it tighter, it's harder to take off the H. And so therefore, it's going to be, this one is going to be increasing acidity versus this one's going to be easier to remove. So the harder it is to remove the H, I guess depends on less acidic. So, sorry, I got it to work while I was talking about the same time. Okay, so when you're increasing the electronegativity, you increase the acidity versus binary acid strength. When you go down, the stronger the bond, the weaker the acid. So HF has a really strong bond, but it doesn't have the difference in polarity that some of these do. So when we do this here, our weaker acids, stronger acids. I'm sorry, my pen's not working now either. So, all right, let me just try, and I'm going to restart my PowerPoint really quick. Give me 1 second. Okay, so I'm just going to restart this for a second, and then hopefully my PowerPoint will work. So the more polarized the bond is, the more acidic the bond is. So the more polarized the bond. Remember polarity, right? Polarity is the difference in electronegativity. So fluorine is the most polar element on our periodic table. So the more polarized it is, the more acidic the bond is. The stronger the bond, the weaker the acid. Right? So the stronger the bond is, the weaker the acid. Because remember, for something to be an acid, the hydrogen ions have to be removed. So that means that the stronger it is, the harder it is to remove the hydrogens. So when we're talking just about like binary acids, just like hydrogen and something else. So as you go across the periodic table, then we increase the acidity. So as you go across, I think that's across for you guys. I think it's opposite than I see. So for example, and this is kind of easy to see. Hold on, let me see. Let's see if this works again. Can you see it again?
Yes.
So as you go across, I only have a part of the periodic table. So as you go across the periodic table, there, now it's working again. As you go across the periodic table, it's going to increase in acidity. And as you go down the column, it's also going to increase in acidity. Now, a lot of times we talk about like acidity, but people are like, oh, this isn't what we normally call an acid. Well, if it starts with an H in these cases, right? We're just talking about binary, where it is an acid. Again, it just might be a weak acid versus a strong acid. So if we look at the relationship between bond strength and acidity, so I'm not sure if in 219 we really did bond strength, but this is just the energy it takes to break the bond. So you can see here that this has a weaker bond. So that means it takes less energy to split up the HBr versus HF. This takes more energy to split it off. So since it's harder to separate that, it's a weaker acid. This one the bond strength is less, so it's easier to take them apart. So therefore, it's a stronger acid. Okay, so again, when we're talking about binary acids, meaning hydrogen and something else, so hydrogen and something else, more acidic as you go across the periodic table because of the polarity. So the greater the difference in polarity, the easier it is to take off that hydrogen. More acidic as you go down the periodic table because the bonds are weaker. Weaker bonds, easier to split. Okay, so those are binary acids. The next one are oxyacids. So oxyacids we have to look at, it's really kind of electronegativity that rules how oxyacids work. It's really based a lot on polarity too. Okay, so the more electronegative the element is, are you guys having trouble hearing me?
No.
No? Okay, let me just make sure my microphone is on the right one. Is this better? Can you hear me better? Or is it the same?
It's the same. I can still hear you. Well, I don't know about everybody else, but you're good on my end at least.
Everybody hear me okay?
I can hear you.
Okay. All right. Just want to make sure. Okay. We're just having lots of technical issues today. It's all right. Okay. So the more electronegativity the element is, so like the Cl, the Br, or the I, right? So the more electronegative it is, it's going to pull the electron density away. So it's going to pull this O, the electron density, away from the O, leaving this hydrogen more exposed. So if the hydrogen is more exposed, that means it's easier to pull apart, right? So what's happening is, for example, we look here, the most electronegative element of these three are chlorine. So chlorine is more electronegative than oxygen. So it's pulling the oxygen's electron density over here, which is making it easier to remove this hydrogen, right? And so that's why it's a stronger acid. Versus iodine, the difference isn't as great, so it's not pulling the electronegativity, the electron difference towards it. It's not pulling the electron density towards it, and so it's going to be harder to remove the hydrogen, so it's a weaker acid. So the more electron densities are pulled away from the hydrogen, more electronegative Y. Easier to remove. So the more electronegative, whatever element is attached, and we're assuming the same number of O's here. We're going to talk about O's in a second. The more electronegative the element is, the stronger the acid is when we're talking about oxyacids. Now, what about if you have more oxygens? So you can see here, these are all chlorates, some kind of a variation of chlorate, like all of our chlorate polyatomic ions, just as acids. So the more oxygens that are attached, the stronger the acid, for the same reason, right? What's happening here is the more O's we have attached, the more electron density is being pulled in this direction, which makes this H easier to take off, right? There's not as much density over here. And so the more O's you have, the stronger it's going to be. So here, this one has 4 O's. It's a strong acid. 3 O's, K is 1. 2 O's, -2. 1 O, -8. So the more oxygens there are, the stronger the acid is because it's easier to take the hydrogen out because the electron density is being pulled this way. Those are supposed to be arrows. Okay. So again, when we look at oxyacids, don't worry about oxidation number right now. What we're just going to say right now is that the acidity of the oxyacids increases as we go across the periodic table. We're going to talk about oxidation number later, but just remember it increases as we go across the periodic table. Okay, so we're going to try these. So least to most. So least acidic, most acidic. Okay, so if we look at this, there's a few things we can look at. So you have to have the periodic table in front of you here. You can't see it unless I literally put it in front of my face. So when we look at the periodic table, we've got AS, P, N, and another P. So we have these two P's. We can directly compare these two, right? This one has 3 O's, and this one has 4 O's. Remember, more O's, more acidic, right? So this one is going to be stronger, and this one's going to be the weaker of these two, right? Then we need to look at these. So if we look here, you have to be looking at your periodic table. We have N, P, and AS. So I'm looking at the periodic table. N, P, and AS. Yeah, we're assuming we don't know that nitric acid is a strong acid, but of course you can always use your like, I know nitric acid is a strong acid, right? So we know that this is going to be the most. And looking at the periodic table, we can see it's the most because it's highest on the periodic table, right? So this is the most. AS is below P, so this is going to be the least. And then when we compare O's, we know that this one is stronger than this one. There we go. Okay. Now let's look at this one. Okay, these are all binary this time. So when we're looking at this one, we know from past experience when we look at these two are similar, right? After we remove each hydrogen, the acid is weaker. So that this means this is stronger, this one's weaker. We know these are both strong acids, but which one is stronger? Is HBr stronger or HCl stronger? That's my question. What do you think? HBr or HCl? Oh, I just got an email that Canvas wasn't working. Which one do you think is stronger, HBr or HCl? HBr. Yeah. So whichever one is lower on the periodic table is going to be the stronger one. Because remember, if it's, let me just go back. I'm going to go to binary acids back down here. So remember, when we're going down the periodic table, the weaker the bond is, the stronger it is. The bonds at the bottom are weaker than the bonds at the top because of the differences in their electronegativity. So HBr is going to be our strongest. Okay, now this time I'm changing it up. This time it's basicity. So least basic to more basic. Okay. Least basic to more basic, right? So that means we're starting with the most acidic to the least acidic, right? Basicity in our brains is a little harder than acids for some reason, right? So we want the one that's going to be least to most. So that means we're starting with the one that has a lower pH to a greater pH. Okay, so which one do you think is the least here? Which one do you think has the lowest pH of all of these? waiting for a second on this one. You got a 1 in 4 chance to keep it. So think of where all these come from, first of all. This comes from HNO3, right? This comes from HNO3, which is a strong acid, right? The conjugate base of a strong acid is pH neutral. So this one has a pH 7, right? So that must mean the rest must be more than 7, right? So then if we go to our next ones, now we have to look at this one. So if we compare these two, this comes from H2CO3. So that's going to be the strongest of the CO3s. Every time we take an H off, it gets weaker. So the next strongest is going to be this, and the next strongest is going to be this. So this one's going to be the most basic of the two, because every time we remove an acid, right, it becomes weaker. So therefore, we know that this should have a higher pH. This should be lower. So we have all those. Oops, sorry. We end up with this. And we're going to come back to these again, right? And so acid strength kind of takes a little bit of it takes a lot of little pieces to kind of understand and be able to put these together. So we're going to keep talking about this to try and make it easier and easier for us. Okay. Oh, that reminds me. I sent an announcement out today that Sonora is going to be able to tutor us. So those of you who weren't in lab today, Sonora has tutored for Chem 229 for years. When you watch those videos in Chem 229, like the videos of the labs, Sonora is the one who's actually holding the video camera, right? So she did like half the editing of it. So she's been working with 229 forever. So if you have any questions on homework, anything that we've done, if you want to go over your quizzes, Sonora is the one to talk to. And she's going to be tutoring like 5 hours a week. She's also doing 209 for me too. But I highly, highly, highly suggest use Sonora. She's really good at what she does. And she's just tutoring my sections. So, and I sent it out. She's going to be available Wednesday, Thursday, and Friday this week. Okay, now, really quick, we're going to touch on Lewis acid bases. I'm not going to talk about these a lot because we are going to talk about these a lot later in the semester. So when we're talking about Lewis acids and bases, we're looking for lone pairs. That's the key to Lewis acids and bases, lone pairs, right? We don't care about hydrogen atoms here. Lone pairs is what we're looking at. So in this case, we have Lewis acids and bases. One donates electrons, one accepts an electrons. So the one that donates is the Lewis base. The one that accepts is the Lewis acid. And we call Lewis bases nucleophiles, and we call Lewis acids electrophiles. And right now, those words don't really mean a lot to you, but in a month or so, they're going to mean a lot to you. But right now, I just want to introduce to you what a Lewis acid and a Lewis base is. You've actually seen these a lot. We just didn't know that that's what they were called. So a Lewis base has electrons that it can share with another atom. So it has a lone pair that it can donate. So that's why nitrogens that's why they're bases, right? So I said at the beginning of this module, I said nitrogens are bases. If you see a nitrogen, it's a base. The reason nitrogens are bases is because they're Lewis bases, right? Because they have a lone pair to give. Generally, the more electronegative the atom is, the less willing it is to be a Lewis base, FYI, right? And anions are better Lewis bases than neutral atoms, just in general. So remember, the most electronegative element is on the periodic table is fluorine, right? So the more electronegative, the less it wants to be a Lewis base. But if it has lone pairs, it can be a Lewis base. Now, Lewis acids, they need to have an empty orbital so they can accept a lone pair. So they have to have the ability to take in a pair of electrons. So So that's why when you took 219 and you did like Lewis structures, and you remember BF3 only had, remember this was BF3? Pretend those are lone pairs right here, right? It only has 6. It only has 6, right? It was an exception to our rule. Well, it only has 6, but remember, it's got space for 8 electrons, but it's only using 6. So BF3 is an incomplete octet. It's got space to take in another pair of electrons. And so therefore, boron is a great Lewis acid. Boron, aluminum's a great Lewis acid because again, that one also has an incomplete octet. So small, highly charged metal cations usually have empty orbitals, and that's why they're really good Lewis acids. And then atoms that are attached to highly electronegative atoms that have multiple bonds are really good Lewis acids. So let's look at boron right now, kind of how it works. So let's look at boron as a Lewis acid and nitrogen as a Lewis base. So you can see here's nitrogen's lone pair. So this is just NH3. I'm just writing it in a different way, right? So this is NH3. That's just how we're writing it. Just so you can see, I want you to see these electrons here. And then boron, again, has that incomplete octet. So nitrogen can donate the electrons to boron. And this thing right here is called an adduct. And again, right now you're like, adduct, whatever, I don't know what an adduct is. It will become important later in the semester. So Arrhenius and bronzofluorate acids and bases can also be Lewis acids and bases. So if I want to show you this one. So this here is called a mechanism. I do not expect you to be able to draw this mechanism. I just want to show you how it works. So here's those lone pairs. Hydrogen will have an empty ability, has the ability here. Here's our Lewis acid to accept that, right, of our HCl. And so you can see here, then this transfers here, and then you're going to see this O is now over there, and then Cl gets kicked off. When you take organic chemistry, you're going to do a lot of these mechanisms, but right now, not so many. Here's what I just showed you before. Here's that lone pair, and boron is going to accept that lone pair, and that is called, again, an adduct. So in this case, which one of these is the Lewis acid, and which one of these is the Lewis base? So is HF the Lewis acid or the Lewis base? Which one do you think HF is? Feel free, you can write it or say it. Yeah. So remember, when we do this, so we go back, our bases have these lone pairs to donate, and the acids have empty orbitals. So they can take in more. What's right there, right? Okay. So now, let's look at this one right here. So this one's a little trickier to see. I'm just going to tell you this one. This one is the acid, and this one is the base. I know it's